Hello everybody and welcome to our first lesson in our unit Introduction to Trigonometry. Today we will talk about some trigonometry basics. Our objective for today will be we will be able to find any of the 6 trigonometric ratios of a right triangle. And now you're gonna say, wait a minute, Mr. Fiese, we have 3 trigonometric ratios, not 6. Well, you know 3 already, but today you will learn about 3 more. First of all, what is trigonometry? We use trigonometry to measure triangles, to measure all the different side lengths and all the different angles of a triangle, and that has lots of applications in real life. It is used in navigation, in astronomy, in construction, and also to analyze periodic functions such as light waves or sound waves, to name just a few. If we have a triangle and it has to be a right triangle, then we can name the different sides with respect to a specific angle. So let's assume that this angle down here is called angle theta, and then the side across from our right angle is the hypotenuse. That's always the case. But the side that is next to our angle theta, that is part of that angle, we call it the adjacent side. And then the side that's across from it is the opposite side. If we have named the triangle like that, we can now go ahead and write our trigonometric ratios. The sine of angle theta is the opposite side divided by the hypotenuse. The cosine of angle theta is the adjacent side divided by the hypotenuse, and the tangent theta is the opposite side divided by the adjacent side. And you have heard this and learned this in geometry, and these 3 you always can remember using the mnemonic SOHCAHTOA. And that is really what it is, because it tells you which 2 sides of the triangle are used for which one of the 3 trigonometric ratios. And now you will meet 3 more trigonometric ratios, but these are nothing but the reciprocals of the 3 you already know. The first one is called the cosecant, and it's abbreviated CSC. So the cosecant of theta is the reciprocal of the sine. That means we just switch the fraction, and it's the hypotenuse divided by the opposite side. Then we have the secant. The secant is abbreviated SEC. The secant of theta is the reciprocal of the cosine, so it's hypotenuse over adjacent. And last but not least, we got the cotangent, and the cotangent abbreviated COT. Cotangent of theta is the reciprocal of the tangent, and that's the adjacent side over the opposite side. Since 3 pairs of 2 out of these 6 ratios are reciprocals of each other, we can also write them as that, and please take note of that going forward. The sine of theta is 1 over the cosecant of theta, and that means that the cosecant of theta is 1 over the sine of theta. The cosine of theta is 1 over the secant of theta. So the secant of theta is 1 over the cosine of theta. And the tangent of theta is 1 over the cotangent of theta. And therefore the cotangent of theta is also 1 over the tangent of theta. How do you best remember which 2 belong to each other? Here's one way to think about it. Each pair has one with a C in the name. Each pair has one and only one function whose name starts with a C. So if we have a triangle, we can find all 6 trigonometric functions using the side lengths of that triangle. But first, we need to, of course, know the side lengths. For this given triangle here, we know that one of the legs has the length of 8 and the other leg has the length of 5. We don't know the length of the hypotenuse yet, but that's not a problem because that's what we have our Pythagorean theorem for. And we can use that to find our missing side lengths. C squared is equal to A squared plus B squared. C squared always has to be the hypotenuse, and that is the side missing here. It's the side across from our right angle. So C squared is equal to 8 squared plus 5 squared. That means C squared is equal to 64 plus 25. And that is 89. So C, therefore, is the square root of 89. And if we look at it, we can't simplify this square root anymore. So that's going to be the side length we're using. Our hypotenuse has the side length of 89. And we have 2 legs. So now with respect to our angle theta here, the leg with the side length of 8 is the adjacent side, and the leg with the side length of 5 is the opposite. And now we're ready to go and can fill in all our ratios. The sine of theta is the opposite divided by the hypotenuse, 5 divided by the square root of 89, but we can never leave an answer with a square root in the denominator, so we need to rationalize the denominator, and the way we do it is by multiplying by a fraction that has the square root of 89 in both numerator and denominator. And so we get 5 times the square root of 89 divided by 89. Our cosine is the adjacent side divided by the hypotenuse, so 8 divided by the square root of 89. And again, we can't leave that, multiplying by the square root of 89 over the square root of 89. We get 8 times the square root of 89 over 89. And again, nothing else we can simplify. So let's move on to our tangent. The tangent is the opposite side divided by the adjacent side, 5 over 8. And luckily, there's nothing else we need to do here. Now let's find the cosecant. The cosecant is the reciprocal of the sine. Now if we take our final answer there and flip it, then we're going to have a square root again in the denominator. Therefore, we're going to take the fraction that we started off with, flipping that. Now we have the square root of 89 in the numerator over 5. That is our cosecant. And similarly, our secant, which is the reciprocal of our cosine, we're taking our initial fraction, 8 over the square root of 89, flip it to get the square root of 89 over 8. And for the cotangent, we flip the ratio we got for our tangent, 5/8, and therefore get 8/5. So if we know one trigonometric ratio, how can we find others from that? Let's look at this example. Find the tangent of theta if the cosine of theta is equal to 5/8. And the way we're going to solve this type of problem every single time, as well as many other similar types of problems in trigonometry, is we're going to draw our own triangle to see what we got. We have a triangle, and it's a right triangle, of course. And down here is our angle theta. If the cosine of theta is 5 over 8, that means the adjacent side is 5 and the hypotenuse is 8. And that helps us to find the opposite side because that's the one we're missing. And that one is also the one we need for the tangent. So let's use our Pythagorean theorem. 5 is one of our legs, so 5 squared plus the other leg, and that is the opposite side, so b squared, the one we don't know, is equal to 8 squared. 25 plus b squared is equal to 64. Now we're going to subtract 25, and b squared is equal to 39. That means that b is equal to the square root of 39, which we cannot simplify anymore. Our opposite side has the length of square root of 39. For our tangent, that means that the tangent of theta is the opposite divided by the adjacent, square root of 39 divided by 5. In our next example, we need to find the cosecant of theta if the tangent of theta is 3 over 7. So let's again draw a right triangle. And if the tangent is 3 over 7, that means that the opposite side has to be 3 and the adjacent side has to be 7. So we need to find the hypotenuse. C squared is equal to 3 squared plus 7 squared. C squared is equal to 9 plus 49. That makes 58. So C is equal to the square root of 58. Another one we can't simplify any further. Our hypotenuse has the length of square root of 58. Our cosecant is the reciprocal of the sine. The sine is the opposite side divided by the hypotenuse. Opposite divided by hypotenuse is 3 over the square root of 58. The cosecant is the reciprocal of that, so that makes it square root of 58 over 3. And here you got your cosecant. The last thing I want us to do today is remember our special right triangles that we learned about in geometry. Our 30, 60, 90 right triangle and our 45, 45, 90, which we also call isosceles right triangle. Remember, we had special formulas to calculate their side lengths. In our 30, 60, 90 right triangle, everything was based on the short leg. So if the short leg has a length of x, the hypotenuse was 2 times that, so 2x, and the long leg was x times the square root of 3. In our isosceles right triangle, we have 2 legs that are, of course, the same length, and the hypotenuse is the length of the leg times the square root of 2. So those were the formulas that we used to find side lengths. Now let's imagine for a minute that we knew that our hypotenuse has a length of 1. What does that mean for our short leg and for our long leg? The short leg is half of the hypotenuse, so the length of that has to be 1/2. And the long leg is the square root of 3 times the short leg. So 1/2 times the square root of 3, or we can also call it the square root of 3 over 2. For our 45, 45, 90 right triangle, if our hypotenuse was 1, then our legs would be 1 divided by the square root of 2. And again, we can't leave that, so let's rationalize that denominator. And we get the square root of 2 divided by 2. That would be the length of both of our legs in the isosceles right triangle. Keeping these values in mind, we can now find all 6 trigonometric functions for right triangles with a hypotenuse of length 1 for specific angles, the angles 30 degrees, 45 degrees, and 60 degrees. And that's what I would like you to do. Now go ahead and fill out this table with all the different values, and we are going to review that together in class. All right, see you there.